Assalamualaikum and a very good day to everyone. Today we're going to continue our discussion for the example number 4 in chapter 2 in your module. For example 4, as you can see, the learning outcome that we are going to cover is quite wide. It's covering 2.1C, D and also E. By now, you should be familiar with 2.1C learning outcome, where you ought to sketch 3 types of graph that are the displacement against time, velocity against time, and acceleration against time. Whereas, for learning outcome 2.1D, you should know how to interpret the graphs. There are the 3 graphs: the displacement against time, velocity against time, and acceleration against time graph. And as for the part learning outcome 2.1E, you ought to know how to determine the distance traveled, displacement, velocity, and acceleration from appropriate graphs given. Okay, let's get into the question for example number 4. As you can see here, you are given a graph of displacement against time. We ought to read the question first in order to decide whether this is a displacement or a distance. Okay, a toy train moves slowly along a straight track according to the displacement. So this is a displacement S against time T graph in figure 2.3. Question A, explain qualitatively the motion of the toy train. So you ought to explain what is going on in the motion. So as you can see here, given to us the displacement against time, like always, I've prepared to you the illustration based on the graph given. So for the very first part of the graph, we can see it in 3 different time zones. As you can see, for the first part, at t equals to 0, our displacement is also equals to 0, meaning that our toy train is still not moving. And then after 6 seconds later, it hits the displacement of 4 centimeter, meaning that from 0, it moves to 4 centimeter away from the initial position. Alright, from time 6 to 10 seconds, what is happening? As you can see, the displacement is not changing, meaning that our toy train remain at the same spot of 4 centimeter away from the initial position for another 4 seconds. That is 6 to 10 seconds. And then, what happened next at 10 to 14 seconds is our train continues its journey from 4 centimeter to 10 centimeter. So, if this is the illustration, as you can see, at time equals to 0, train is at starting point, s equals to 0. And then, 6 seconds later, it reaches 4 cm. After 6 seconds to 10 seconds, it remains at the same place of 4 centimeter away from the initial position. And then, after 10 seconds to 14 seconds, it continues its journey to 10 centimeter away from the initial position. Alright, if we do understand the situation, it shouldn't be a problem for you to explain qualitatively what's happening to the train. Alright, so as for me, I love to explain it in time zone way, so that you can understand it better. So you see, 0 second to 6 seconds, what happened to our train? Our train moves with constant velocity. Okay? And from 6 seconds to 10 seconds later, our train stops. As for the next one, from 10 seconds to 14 seconds, our toy train moves in the same direction, but with, once again, constant velocity. As you can see, I just use constant velocity here because we didn't being asked to calculate the exact velocity of the train each time it moves. Okay, so that's for part A. moving on to part B of the question. Sketch a velocity against time graph. So for velocity against time graph sketching, once again I've prepared to you. You want to focus on this part first, alright? So this is a velocity against time axis. So for the very first part, as you can see, from the earliest graph that we're given, that is the displacement against time, we've been given a linear graph, alright? A uniform linear graph. For us to have the velocity against time graph, actually we should be differentiating the first graph. So from a linear, it will transform to a constant graph. What do I mean by a constant graph? Okay, let's see together. So for the first time frame, that is from 0 to 6 seconds, what happened is our toy train moving with a certain constant velocity. So I'll show you the very first calculation here, where the first velocity is equivalent to change in displacement divided by change in time. That's from here I managed to get the first velocity of 0.67 centimeter per second. So that's why I've drawn the first line of the graph, that is for 0.67 second, from 0 to 6 seconds of time. And what happened to the second time frame? The second time frame happened when our train decided to stop at the point where the displacement is equals to 4 centimeter for another 4 seconds. So making the velocity as 0, because it stops, velocity is 0. That is why here from 6 to 10 seconds, our velocity is 0. Alright, then for the next one, 10 to 14 seconds, our train continues its journey, and then we ought to find the velocity from the gradient of the first graph. Okay, so the gradient of this part, you should be calculating for the gradient, meaning that delta S divided by delta T. Alright, so making it 10 minus 4 divided by 14 minus 10. So we will get the value of 1.5 centimeter per second. So here I've labeled 1.5 centimeter per second. So this is a constant graph where we have only straight lines without gradient. Okay, so this is for the second part of the question, part B. As for part C and part D, I'll continue it later in the second part of the video. Hope you understand it so far. Thank you very much for watching.